So that's the topic, and the sort of things I'm going to talk about in this short session are, well, I suppose it's a pretty cheery little list really. It's things like climate events, it's things like flooding, fires, volcanoes, landslides, acts of terror, and the impact that they can have on the way that we manage our infrastructure in response to those types of events. So I'm really going to focus, there's obviously a lot of different approaches that can be taken there related to even the broader topic of instrumentation and monitoring, but I'm really going to focus on a smaller subset of that around the topic of wireless remote condition monitoring. In this session, I'm just going to spend a few moments looking at the definitions and the context and the challenges that we're facing in this arena. But I want to spend most of my time hopefully looking at some projects, some case studies, some places from around the world where people have used this technology and the benefits of its flexibility and responsiveness to help to mitigate the risks of these events, to mitigate the impact and to protect people and infrastructure. So there are different types of event that can have an adverse effect on our built environment, on our bridges, our tunnels, our railways, our roads. I'm not going to go through them all, but if we just focus a little bit on the problem, the impact of a changing climate on our infrastructure. I don't think it's going to be a surprise to anybody in the audience that the shape of that graph, we are dealing with a warming climate. According to many records, last year was the warmest globally on record, or on average. And we're seeing us approaching that 1.5 degrees warmer environment than the pre-industrial era. 1 degree of warming can relate to 7% increase in rainfall. Warmer air carries more water, and that can manifest in not just a little bit of light drizzle spread over long periods, but because it injects more energy into the environment, it can manifest in bigger storm events. It can manifest in extreme periods of rainfall that we haven't typically dealt with before in our infrastructure management models. So it's having an impact, and I think we're becoming almost accustomed, perhaps almost too accustomed, to seeing stories of the impact of these types of events, of violent storms or extreme periods of rainfall, on people and on the infrastructure that they rely on for their habitats, for their transport, for their energy generation. So in that sort of context, I think we need to explore what can be done. Now, as much of an advocate as I am of wireless condition monitoring, I'm not suggesting that we're solving this problem, but I am suggesting that we're adding a useful tool into the armory, into the toolbox of people who are responsible for that sort of an issue. And I think that people can use it in three ways. They can use it in an early stage, a proactive way to predict an event before it happens. And if that installation has happened in the right place, using the right instruments, they should be able to detect when an event such as a landslide takes place. And that's extremely useful. In reality, we don't know. It's very hard to prioritize every vulnerable asset, every at-risk bridge, tunnel, slope. So in reality, we have to look at options to gather data quickly after that bad thing, that event has taken place. So all three of these places, I think, are situations where instrumentation and monitoring has a role. And if we look at those first couple, I think a great example of that is the way that Senceive engineers have worked with network rail engineers in recent years to develop a solution that comprises thousands of tilt sensors. Around about 30 to 40,000 tilt sensors are now installed on network rail's slopes, on their cuttings, on their embankments, and they're fitted into an integrated solution with some smart software, some all light level cameras that sends automated alerts when the early signs of a landslip affecting the railway asset takes place. So if you know where the most vulnerable places are, if you can prioritize the 30 or 40 kilometers of the 10,000 kilometers of the UK mainline railway network that are most at risk, you can do this. And that's a great approach, and it is proven to protect people and infrastructure. But it's really not practical to do that everywhere. So we need to focus a little bit on what we can do when that thing happens, how we can react. And that really, for the rest of this session, is where I want to spend my time. How we can take tools that are fast and flexible, and how we can react quickly to the event. And I think reactive monitoring needs to be probably at least three things. It needs to be fast. We need to be able to respond quickly, get to the location, and we need to be able to install some equipment. We don't need to rely on highly skilled surveyors. We need to be able to do it with the people and the resources that we've got available. So the technology needs to be fairly simple, and it needs to be operational quickly so we can see the data. And we don't always know exactly what we're going to be having to monitor. We could be looking at a flood event affecting a building. So there could be washout of foundations, there could be cracking of the masonry, there could be extreme loading on structural elements such as beams holding the building up. So if we've got a range, a menu of different sensors that can be incorporated into a system, we're in a better place. And if we've got that ready to hand, it can be installed, we can collect the data that we need to look at the loading on that beam or the stability of the foundation. So flexibility is important. And I think the third factor is that it needs to provide the right information. We need insight, we need data at a high frequency rate. We need to be able to look at the stability of vulnerable structures that have been exposed to a problem in a frequency that is going to tell us if they're continuing to move. And we need that data in useful terms of measurement. We need movement in terms of millimeters. We need strain in engineering terms. We need to understand what's happening in language that we can understand and that engineers and building owners, asset owners can respond to. So an approach that a number of people have taken around this field is to look at basically putting some equipment on the shelf in their office, or on the shelf even in emergency response vehicles. If you're looking after a response contract for a railway operator, for an infrastructure owner, then a number of people around the world are now taking the initiative. They are buying a big Peli case and filling it with a range of equipment that may be required in the event of one of these events taking place. So the sort of thing they might be stuffing in that box, and it will vary depending on the need and the nature of the situation, the sort of kit they might do and fit a range of sensors, maybe a camera. They will need a communications gateway so that you can collect that data and get it through the mobile phone network, or if you've got an internet connection, which is unlikely to the user. A web, an access to a data portal so that you can see the information, an ability to customize and be flexible about how that's used, and it needs to be kept powered up. It needs to be kept in a situation where it's ready to go. It's no point mobilizing a team and saying, oh, we have to wait 12 hours to charge the batteries up. It needs to be ready to go. And the sort of sensors that can be included in that, again, these will be varied depending on the need, but they can include tilt meters that measure rotational movement to 1,000th of a degree. These can be installed to virtually any surface, any type of material, any orientation. They don't require calibration. They can be as simple as mag mounted onto a steel structure, and they will be providing data to that web-based portal within minutes of being installed. They don't need particularly skilled, trained people who are familiar with the technology, but they do need, a basic level of understanding, a little bit of initial sort of guidance and training. We can measure displacement between different objects. We may be able to fix a laser displacement measurement sensor, an optical displacement sensor, to a solid object outside our zone of concern and directed a building, a bridge pier, a structure that we're concerned about, and look at the relative displacement between those two surfaces without having to put anybody in that danger zone. And we can leave it there and it will be working within minutes, and it will be operating potentially for years after we've put it there. So this is really simple kit to install, and it provides us with very valuable data and a real-time, virtually continuous data stream without having to touch and feel and climb over the structure we're interested in. And as I say, we can collect, we can engage other sensors to look at movement of joints or displacement across a crack in a building. We can collect engineering parameters data, such as stress and strain and load, and integrate even with geotechnical sensors to look at piezometers to look at groundwater pore pressure or flow, various things in various borehole data. So it's a flexible package of sensors. And very often people looking at this situation will be interested to combine a digital camera with this, and if they use the InfraGuard solution that Network Rail have employed to such effect, then that camera can be automatically triggered by a threshold breach in one of the sensors. So if a movement sensor moves beyond a preordained threshold, a camera image can be taken and the user can be not just woken up by an alarm on a wet Saturday night when they're in bed 100 miles away, but they can actually see a picture to determine whether it's a reason to get out of bed or whether it's a false alarm. So that can save an awful lot of stress. So that's a little overview really, I think, of the challenge, the need for monitoring data, the way that it can help to mitigate the risk and deal with the response. I now want to look at, I don't know, 5 or 6 examples really where people have put that kind of approach into action. The first of these is relatively local and relatively recent. It's a little site on the East Coast Main Line where the fine team at SEP Rail Services, who are engaged with Network Rail as part of their emergency response setup, and are very experienced and adept at dealing with things like washed out embankments and failed landslides affecting slopes. And part of their approach has been to embrace this technology. So this example here was a relatively small scale but significant washout failure of a relatively shallow embankment on the East Coast Main Line. Clearly it's affecting the stability of the track, and there's a big question about whether trains are fit to be kept running on that section of track. An immediate design was put into place to put up shoring in the form of this continuous sheet piled wall. But during that work, and even before that work started, I think within 24 hours, a monitoring installation was set up at that site, really with the simple objective of determining whether or not it's safe to keep the trains running. And that was set up before the groundwork contractors were on site there, and it was monitored through their works. And the data was set up, and this is with a combination of tilt sensors. You can see here that one of them is just simply mounted with a magnetic mounting onto one of the overhead electrification gantries. Very, very simple, instant setup really, to see whether that gantry is continuing to move after the event. And it's done in combination with a total station conventional topographic survey. So the two things work well together. And in this case, my understanding is that the site was pretty dynamic, it was pretty funky, there was a lot of movement going on, but they were able to look at the data pattern, the pattern in the data, the movement cycles in the data. They actually adapted their installation of the sheet piling as they were looking at the virtually real-time data coming through. They were able to respond to that, adapt to their working pattern, change the approach, and the trains were just kept on a slow, but the line was kept open through the large part of this work. So disruption was very much minimized as a result of this. So the next example is a little bit further afield. This is the Roya Valley, which is a mountainous area between the border of Italy and France. And in October 2020, it was subject to a very heavy rainfall event, severe flooding, cut off a number of villages, it damaged bridges and buildings throughout the region, and in particular it caused a problem with this regional hospital that you can see highlighted here. This is the Saint-Nazaire Hospital. Around about 65 patients were evacuated as a result of this flood, but the building was left in a rather precarious state. There was washout of the ground surrounding some of the foundations. A number of terraced balconies were left hanging in mid-air that were previously sitting on the ground. There was quite a lot of cracking on the front elevation of the building, and there was significant concern initially about whether it was even safe to go into. So this was a situation again where one of the partner companies of Senceive, GEO, again experts in this type of work, looked at it. They looked at options to install a conventional kind of topographic survey setup, laser scanners. They looked at wired monitoring solutions, but just too complicated. A wireless solution fitted much better here. And in that sort of inaccessible, dangerous site, and you can see here one of these terraced areas that was previously sitting on a nice firm bed of ground, hanging in midair now with those three piles. So they implemented this wireless solution, getting data every 15 minutes from tilt sensors installed on the foundations and on the building, and this allowed them to get data every 15 minutes, 7 days a week, 24 hours as the repair work was carried out. So in the first instance, it gave people the confidence to actually send people in to do a study of the building, to get in there, to do the first sort of response. And then throughout the construction period, the repair period thereafter, and I think this went on for at least a year afterwards, that monitoring was still used in that period. Different sort of application. This is a dam, a relatively small regional dam located in Vermont, East Bar Dam. The significant thing here is that although it's relatively small, it is located just up a valley from the town of East Bar. So there's actually quite a lot of people who are pretty much got a vested interest in the integrity of this structure, which, as you can see here, is not particularly great. There's a significant amount of movement, displacement occurred in a relatively short period, in a matter of days or weeks. These two panels managed to slide apart from each other, and there was obviously a reason for concern about whether that movement would be ongoing. So in this particular case, after that was seen, they took an approach there where they installed a number of different things. They installed a camera, they installed a gateway that sent data back to the users, and you can see here this is the camera, the gateway, and a solar panel. We're dealing with pretty much extreme temperatures here. Vermont in the winter down to -30, relatively short hours of daylight. There is still enough power harvested by that solar panel to power that camera and the gateway that transmits its data. So they'd also installed tilt meters onto the panels, and also displacement sensors on objects further away, looking at it from a distance. But I kind of like this image. It's a mono image. Our cameras are mono. They work any hours of the day in any daylight condition, but it brings home the sort of bleakness, the coldness of the site. And I kind of picture the engineer who's responsible for this not having to go out to site at -30 in the middle of the night, being able to look at the picture instead. But as it happened, after that initial period of movement, very little else happened. The sensors that were installed actually showed that it very quickly settled down, and it was then left for a period through to the summertime with the confidence that it had got this incoming data before repairs were carried out in a slightly more hospitable time of year. So in that case, it proved that the structure was still okay, and that the situation could be managed thanks to the monitoring data. So I think everyone's going to be familiar with the fire that destroyed the roof, destroyed the spire of Notre Dame Cathedral 5 years ago now. So, amazing symbol of French culture and architecture, and Gothic architecture throughout the world. And I think everybody was shocked when they saw the images and the live TV at the time. And certainly the challenge that the engineers faced in the immediate aftermath of this was really, really significant. They were dealing with obviously the effects of the fire that had completely removed the timber roof that you would have previously seen if you were looking up from the nave. It was the stone arch structural roof above the timber was left exposed. It had been subject to extreme heat. It had been subject to cooling from the fire brigade water. And there was a great deal of concern about whether that roof was going to stay up, or whether it could take any additional load. There were quite a lot of additional bits of stone and timber that had fallen onto it from the spire and from the walls above it during the aftermath of the fire. And nobody was even allowed to tread on it. A monitoring solution was needed to determine if it was stable, if it was continuing to move, but no load was allowed to go on it. So hence the team from Osmos here, again French specialist in instrumentation and monitoring, used rope access technicians to install these very, very small nano tilt sensors. There they are. Just with a little bit of adhesive. No, actually, you weren't allowed to use conventional adhesive. They had to use a lime-based putty, a lime-based mortar, and a really neat solution to this very vulnerable, very precious environment. They were kept safe because they were suspended from structures above, and there was no additional load onto the structure. And they were used again in the immediate aftermath, in the days after the fire, but they were used throughout the period of years after the fire as well. And you can see here how that worked, and the data from some of those tilt sensors, how they were installed in various places around the arches of the tower. And I think we probably remember that President Macron made this bold statement in 2019 that it would be ready and open for the Olympic Games this summer. And well, the spire opened, the new spire opened in February this year, it's not fully open to the public, but I think it's due to be by the end of this year. And certainly from the outside, a lot of the scaffolding has now been removed, and it's really looking rather magnificent again for all of the visitors that will be there this summer. So we played a small part, I think, very small technology, playing a small part in, really globally significant project, I think. Quite a thrill. And the last one I just want to close with here is that the earthquake, again, people will be familiar with this, is an event in the recent past, 2023, in February, 7.8 magnitude earthquake hitting a pretty broad area of southern Turkey, particularly having a devastating impact on the city of Gaziantep. And enormous scenes of damage and a lot of stories of loss of life and harm to people. And again, this is just an example. I wanted to show how different people use this sort of IoT technology in different ways. In this particular case, emergency response people, this is after all a seismically active area with a high earthquake risk. And preparations, are fairly well made in these types of area in the world. So in this area, again, equipment had been bought in advance. People had done some training using this equipment, and the emergency response vehicles that dealt with various aspects of these types of events actually had small wireless monitoring kits installed in them, and they were set up to have displacement sensors, optical displacement sensors, up on these masts of these vehicles, so they could be moved to a site of interest and parked, and they could be staring at a building of concern, particular concern, maybe one where there's maybe a risk where there are still people in there, and they could be looking at ongoing movement of that structure. So that again is quite a neat, rather different solution to the way that this sort of technology can be used. I hope that there's some quite different things there, from network rails earthworks to Gothic cathedrals to fairly ordinary looking small concrete dams, to a response to tragic and shattering earthquake events. But that made a mark, obviously, in many ways. But one of the notable things was that it was one of the few occasions in my experience where tilt sensors and optical displacement sensors have made the national news. This was actually featured. The data from these, it's a bit fuzzy up there, but the data from the wireless sensors was actually shown on Turkish national evening news there as part of the response.